Mathematics is essentially a language of translation. One of its oldest problems is taking an infinite set of geometric points in space and mapping them into a single, finite equation. We are developing the ability to reconstruct visual geometry from algebra and to find the algebra within the geometry without the aid of external software. To do this, we have to understand the dual nature of a polynomial. Its shape is dictated by two distinct sets of rules: local behaviors and global limits. The local rules define the points where the curve interacts with the axes. We call these intercepts, and the specific way the curve passes through them is governed by a property called multiplicity. But when we zoom out to the extremes of the graph, where the numbers approach positive and negative infinity, the curve is instead controlled by its global behavior. We will first construct a visual graph directly from a factored equation, and then reverse the process, deriving an exact formula from a raw graph. This process shows that the specific path of the curve is a direct expression of its algebraic components, where every visual interaction follows a specific mathematical rule. We begin the forward mapping phase by analyzing this specific equation. f of x equals negative the quantity x plus 2 squared times x minus 5. On a Cartesian grid, we extract the polynomial's structural skeleton, the roots. The factor x plus 2 provides our first geometric point, an x-intercept at -2. The second factor, x minus 5, gives us another anchor at +5. We must know the geometric behavior at these points, dictated by the exponent. An even multiplicity, like the power of 2, creates a localized parabola bouncing off the axis. Conversely, an odd multiplicity, like the exponent of 1, forces a linear path crossing the axis. These roots and their localized behaviors form the internal framework of the graph. The curve is constrained by these rules at the x-axis before it travels anywhere else. With the internal skeleton set, we shift to the global limits. Where does the curve originate, and where does it go at the boundaries? End behavior is controlled by the leading term. Expanding the variables isolates the term, negative x cubed. As the input approaches positive infinity on the right, the output plunges to negative infinity. Moving left toward negative infinity, the cubic outputs positive infinity. To anchor the curve, we substitute 0 for x, yielding a precise y-intercept of +20. Connecting the components, the continuous line descends, bounces at -2, passes through 20, crosses at 5, and continues to negative infinity. By following the algebraic rules for roots, multiplicities, and limits, the winding shape of the polynomial is forced into existence. This method relies on having a perfectly factored equation. But in many applications, polynomials are not presented in clean factored forms. If we cannot factor the algebra to find the exact roots, we need a way to prove that a curve crosses the x-axis at all. We solve this with the Intermediate Value Theorem, a law that applies to all continuous functions. A polynomial is a continuous function, meaning it is an unbroken curve that can be drawn from end to end without lifting from the plane. The theorem states that if 2 points, A and B, have opposite signs, a specific event must occur. Because the function is unbroken, it is geometrically impossible to travel between them without crossing the x-axis at least once. The intermediate value theorem is vital because it proves the existence of a root through the analysis of positive and negative spaces, even when exact algebra is difficult to calculate. We can now reverse the process, taking an unlabeled visual curve and deriving its hidden algebraic formula. To reverse engineer this target graph, we scan the curve to identify the intercepts. We see roots at -2 and +1. We translate these back into their algebraic factors, giving us the skeleton, x plus 2 multiplied by x minus 1. Next, we observe the geometric behavior at each root to determine multiplicity. The curve bounces at -2, mapping to a squared term. At +1, it crosses cleanly through, mapping to an exponent of 1. This skeleton dictates the shape and intercepts, but there are infinite curves that could share this shape while sitting at different vertical scales. We must determine the specific height of the curve by applying a stretch factor, denoted by the unknown variable a. To solve for a, we pick one discrete coordinate from the visual grid, in this case the y-intercept at 0, -2. By substituting 0 for x and -2 for f of x, we find that a equals 1/2. This provides the final calibrated equation. By combining the structural framework of the roots with a single precise coordinate, we can flawlessly define an entire infinite curve within a few algebraic terms. The relationship between algebraic formulas and visual space is entirely deterministic. Our mappings are now complete. Roots correlate to factors, local shape correlates to multiplicities, and the boundaries are set by the leading term. However, this toolkit has a limit. While it identifies the intercepts and the boundaries, it cannot precisely map the peaks and valleys between them. We can calculate the maximum number of turning points by looking at the polynomial's degree, but finding their exact coordinates on the grid requires a different mathematical approach. Locating the exact position of these turning points marks the edge of what algebra provides, signaling the transition into the domain of differential calculus.